Now let us see some of the classifications of signals. First we will see about one-dimensional and multidimensional signals. So one-dimensional signal means there is only one independent variable. So it looks something like, so in our case we consider time as our independent variable. Signals in general is function of one or more independent variable. So if the signal is a function of just one independent variable, then we can say it is one-dimensional. Any higher than that, we call it as multidimensional. An example for a two-dimensional signal could be y equal to f of x comma y. So this can be extended to any dimensions. Now deterministic signals are signals whose values are specified for any given interval of time. So its values are specified in any given period of time or given interval of time. Or we can say its values can be determined. Non-deterministic signals are signals whose values cannot be specified. For example, random signals or random noises are examples of non-deterministic signals. So we cannot determine what value a random signal may take at the next moment. So they are non-deterministic. And deterministic signals, on the other hand, are well defined and the values of it can be specified in any given time. So we have already seen about continuous time and discrete time signals. So continuous time signals are signals where the independent variable is time and it is continuous. On the other hand, discrete time signals can be considered as functions of integer variable n. In our case, we use t to represent that it is a continuous time signal and n to represent that the signal is discrete time. So if we write x of t, it will represent a continuous time signal, and on the other hand, if we write x of n inside square brackets, it represents a discrete time signal. We will discuss a lot about continuous and discrete time signals in coming videos. So an example of continuous time signal could be a speech signal whose amplitude may take some values like this. So this is an example for a continuous time signal. Now let's take a look at discrete time signal. So when representing a discrete time signal, we have an integer variable, and this discrete time signal takes values only at integer values of argument. So n here will be integers in the case of discrete time signals. We are familiar with periodic signals. Now periodic signal, it completes a pattern within a measurable time frame, and we call that time frame as a period. And this pattern is repeated over subsequent periods. Let's take a look at some of the examples. So these are all examples of periodic signals. Here it's visible that this is one period of the signal and this gets repeated throughout. This is a familiar waveform, it's called a sine wave. So this is one period here. In this case, this is the one period. Here this is one period of the waveform, and this is also a periodic waveform. Here the period is marked. This is one period of the waveform. Now non-periodic means there is no such pattern and there is no concept of period in the case of a non-periodic signal. Now let's talk about symmetric and antisymmetric signals. So in the case of a symmetric signal, if you look from this point here to the right or left, the signal will look the very same. Now in the case of antisymmetric signal, if you flip one of these sides, you will get a symmetric signal. Now there is a mathematical way to check for symmetry and antisymmetry. We will discuss about it later after we have seen some of the manipulations in time domain like shifting, scaling and so on. Now in the case of discrete time signals, this is what a symmetric signal will look like. So this is a symmetric signal in the case of discrete domain, and this here is an example of antisymmetric signal. Now let's see about causal and non-causal signals. Now this signal here, let's say x1 of t, it is 0 for t less than 0. Such signals we call it as causal signal. So this is an example of a causal signal. Now if the signal has some value for t less than 0, we say that the signal is non-causal. So here we have values for the signal for t less than 0. That means if the signal is not causal, we can say it is a non-causal signal. Now this is another interesting class of signals. It is called anti-causal signal. Here the signal value is 0 for t greater than 0. So this is an example of causal signal. This is an example of non-causal signal, and here we have an example of anti-causal signal. So causal signal means the signal value is 0 for t less than 0, and if it is not causal, we can say it is a non-causal signal. And anti-causal means x of t is 0 for t greater than 0. Now for the sake of completion, let me mention about energy and power signal. So energy signal are signals with finite energy. So if the signal energy is finite, we can say that the signal is an energy signal. So similarly, power signal will be having finite power. So we will discuss about how to calculate energy of a signal and power of a signal at a later stage, and we will have a detailed comparison between energy signal and power signal. For now, energy signal is signals having finite energy, and power signals are signals having finite power.